All right, I think this is one of the homework problems. Triangular loop of wire carries a current, so it's a loop of current. And my question for you, and so there's a force on each piece of the current. That is what? I dl is the direction of the current, cross with B. That's just like the V cross B, I times dl. It's just V. So you know something about, I think you know something about current loops in a magnetic field. We've talked about this before. It turns out if you have a loop of current in a uniform magnetic field, then there's no net force. But there still can be a net torque. So my question for you here is, what's the direction of the net torque? Now, it has so much right-hand rule in it that you'll have to take your time, because all of the forces are going to have right-hand rules to try to figure out the forces on the various pieces. Once you have the forces on the various pieces, if it's trying to rotate this way, then it's a torque to your right. If it's trying to rotate this way, then it's a torque to your left. If it's trying to rotate this way, then it's a torque downward. So there's a right-hand rule to figure out the torque after you've done all of this other stuff. And so I'll let you to it. Talk about it all you want. I'll probably give you some more time because it takes a little while to go through this step by step and figure out all the forces and figure out the torque direction. Uniform magnetic field points up the screen.
It's like half.
I better do this too, or else I'm going to have to do it while you're already finished.
If you like assume that they all
So you're running out of time. So there is a main answer, and I'll have to think about this carefully, although that main answer is the answer I got when I just did it quickly. So let's see. First of all, magnetic field points up the screen, and so the vertical piece of the loop on the left has no force because I is along the magnetic field. The horizontal piece at the bottom and that angled piece at the top of the loop both have forces on them. If your V finger points to the left for the bottom piece, and your index finger points up for the magnetic field, you see that the bottom piece has a force the horizontal bottom piece has a force into the screen, And just because the current is in a different direction, I can then conclude, although I can check it, that the force on the angled piece at the top of the screen has to be out. So the force is outward. And so inward at the bottom, outward at the top is something that you're trying to rotate like that. And that kind of rotation gives you a torque vector pointing to the right. Yeah.
Does it matter that when it's playing, like when it turns like 90 degrees, like the vertical power will have a force on it, pushing it
It does matter for its eventual motion, but the torque as it stands right now points to the left. But you're right. As soon as it starts to move, then in some sense all bets are off. What you calculated has to change. It'll change as it moves. You probably know that this loop is a magnetic dipole. A loop of current is a magnetic dipole. The magnetic field, due to these pieces of the loop, points in the middle of the loop, points into the screen. Because the magnetic field points into the screen, our side of the screen is the south pole, where the magnetic field is coming in, and the back side of the screen, this side of that loop, the back side is a north pole, where the magnetic field is coming out. And so I'll just leave it at that. So I got to the right, and most of you got to the right. Let's pretend that that's correct. Probably is. Any questions about that one? So how do you find out the total force or total torque? Well, you have a force equation. DL cross B doesn't change anywhere along one of these wires, and so that just becomes the length, the total length. If you integrate along this wire to get the total force, you'll get the total length times the current times the magnitude of the field. For this one, you'll get 0, and for that one, it turns out it's the opposite force to this one, and you can check it, but it comes out that way. So no net force, because the forces on the bottom and the top are opposite, but a torque.